Today I will show you how you can calculate the eigenvalues of a 3 times 3 matrix faster and easier. Let's take a look at the following example. We want to find the eigenvalues of this matrix here. So because this matrix has lots of non-zero entries, it's not the best idea to try to find the characteristic polynomial here. Let's try a different approach. Basically, we will try to guess one eigenvalue by just looking at the matrix A. Most tasks will be constructed in a way that there is at least one integer eigenvalue that can be guessed without too much thinking. By the way, this also has a more mathematical explanation and works with the fact that A has only integer values as entries. Okay, enough of that. I will now show you how it works. You have to subtract a number lambda 1 from the diagonal entries of A in a way that the resulting matrix doesn't have a full rank. I've written this down here again. So we have to find an integer number lambda 1 in a way that when we subtract it from these diagonal entries here, we get a resulting matrix that has a rank that is smaller than 3. If we now take a really close look at the structure of our matrix A, we will see that this works out for lambda 1 is equal to 1. Why is this so? Because when we subtract 1 from the diagonal elements of the matrix A, we will get the following. So we are subtracting 1 from the diagonal elements of A. So 2 minus 1 is equal to 1. 2 minus 1 is equal to 1. And 3 minus 1 is equal to 2. And now when we take a look at the first row and the last row of this resulting matrix, we see that these two rows are identical. This means this matrix here doesn't have full rank. So the rank of this matrix is not 3. And this is the condition here. So lambda 1 equal 1 fulfills this condition here. That means we have guessed our first eigenvalue lambda 1 is equal to 1. So this here, lambda 1, is our first eigenvalue, and we have guessed it by using this condition here. If you have problems finding such an educated guess for the eigenvalue lambda 1, the following could help you. If there exists an eigenvalue lambda 1 that is a whole number, which in most tasks will be the case, this value has to divide the determinant of A. So in symbols, this value lambda 1, which is the guessed eigenvalue, has to fulfill lambda 1 divides the determinant of A. So lambda 1 has to divide the determinant of A. So you only have to check the positive and negative divisors of the determinant of A. They are your candidates for integer eigenvalues for guessing. And you won't do extra work when calculating the determinant. You will need it in the next step anyways. So now we will calculate the other two eigenvalues. If not happened in the guessing process before, we now need to calculate the determinant of A. In our case, the determinant of A is the following. So the determinant A is equal to. So we have 2 times 2 times 3 is 12 plus minus 1 times minus 1 times 1 is 1 plus 2 times 2 times minus 1 is minus 4 minus 1 times 2 times 2 is minus 4 minus 1 minus 1 times minus 1 times 2 is minus 2 minus 3 times 2 times minus 1 is plus 6, and therefore we get 4, 5, 3, 9 for the determinant of A. We also need the trace of the matrix A, which is very easy to calculate because the trace is simply the sum of the diagonal entries of the matrix A, which is 2 plus 2 plus 3, so 7. Equal to 7. This is the trace of A. Now we have to write down another two numbers, which we call P and Q, where P is equal to, so P is equal to the guessed eigenvalue lambda 1 minus the trace of A and the second number Q is equal to the determinant of A divided by lambda 1. So this fraction here. Okay, now we have to calculate these two numbers, P and Q. And we already know what lambda 1 is, because this is our guessed eigenvalue. And we also know what the trace of A is and the determinant of A, because we have calculated determinant and trace here. So let's calculate P and Q. So here we have lambda 1, which is 1. And here we have the trace of A, which is 7. And 1 minus 7 is minus 6. And here we have the determinant of A, which is 9. And lambda 1 here is just 1. So we get for Q the number 9. Now we will use these two values, P and Q, in the PQ formula, which you may already know from school. The PQ formula is this formula you use to calculate the zeros of a polynomial of degree 2. So we use these two values here, P and Q, in the PQ formula, and this leads to our other eigenvalues. So for lambda 2 and 3, we now get minus P half plus minus the square root of this number here squared minus q. By inserting p and q, we now get minus 6 half. With a minus sign here, we get 3 plus minus the square root of this number here squared, 9 minus q, which is 9 too. So in the end, we get for the other two eigenvalues that these two eigenvalues are identically and they are 3. So the other eigenvalue is lambda is equal to 3 and it has multiplicity 2. Okay, now we have found all the eigenvalues of the matrix A. So here we have the first eigenvalue, which we guessed, and here we have the other two eigenvalues, which are actually just one eigenvalue with multiplicity 2. Okay, let's summarize the approach up again. So the first thing we have to do is to guess an eigenvalue lambda 1. To do so, we have to subtract a number from the diagonal elements in a way that we get a resulting matrix that has not full rank. So in our case, this educated guess was lambda 1 is equal to 1. If you have problems finding this number lambda 1, you can use the fact that every integer eigenvalue has to divide the determinant of A. You also see this here. The newly calculated eigenvalue 3 here is an integer eigenvalue, and this integer eigenvalue divides the determinant of A, which is 9, and 3 divides 9. This is exactly this condition here. It is true for every integer eigenvalue lambda. The next step is to calculate the determinant and the trace of A. When you have these two values, you can insert these two values in these formulas here to get P and Q. The last step is to insert P and Q in the PQ formula you may already know from school, and then you get the other two eigenvalues, lambda 2 and 3. Okay, I will talk about two last things. The first thing is, you may have already noticed what happens when the guessed eigenvalue lambda 1 is equal to 0. In this case, you will get a problem when you have to calculate q. When the guessed eigenvalue lambda 1 is equal to 0, you have a division by 0 at this point. So you can't calculate q when using this formula here. So in the special case lambda 1 is equal to 0, you have to use another formula for the calculation of q. In this special case, q becomes the sum of the 2 times 2 principal minors of the matrix A. But maybe I will make another video where we'll talk about the special case lambda 1 is equal to 0, and also will show you how you can calculate the value q in this special case lambda 1 equals 0. The second thing I want to talk about is that all this only works out because the matrix A has only integer values as entries. I also have to tell you that it could happen that this guessing process here fails, so that you won't find an integer eigenvalue lambda 1. But as I told you before, normally such tasks are constructed in a way that there is always at least one eigenvalue lambda 1 that is an integer which can be guessed, because such tasks are considered to be solvable by hand. But even if the worst case happens and you can't find a nice integer value for lambda 1, for example, when you have tried out every divisor lambda 1 of the determinant of A and still haven't found an eigenvalue lambda 1, you have still options. For example, you can take the determinant of A, which you have calculated before, together with the trace of A, and another value, a third value, the sum of the 2 times 2 principal minors of the matrix A, and then with these three values you can write down the characteristical polynomial directly, and then you can try out to calculate the zeros of this characteristical polynomial. So this would be another option when this case happens. Okay, whatever. Maybe I will make another video about it, but probably not. Whatever. Thank you for your attention.